Yes, class, am I audible to you? Alia, Harsha?
Yes, ma'am.
Okay. So two types of moduli of elasticity we have already discussed. One was Young's modulus, which was the ratio of longitudinal stress by longitudinal strain, means the change was there in the length. Secondly, we had seen bulk modulus, which was volumetric stress by volumetric strain, and it was due to the change in volume. Last one, which was the change in shape, that was left to be discussed, which is known as the shear modulus. Now, shear strain we have done, shear stress we have done. Shear stress means the tangential stress. Remember, I gave you an example. If you take a book and if you just slide and apply a slight force in the upper part of the book, it becomes like this. The book which was kept like this, base remains at its own position, and it gets shifted a bit. So there's a change in shape, and now the force that is applied, the tangential force upon area, we call it as tangential stress. And the theta, the change that is coming, this theta, this we call as tangential strain. So when we are talking about, tangential stress will be equal to force divided by area. This force which is being applied parallel, and tangential strain is change in length by original length, change in dimension by original dimension. So we represent shear modulus with the symbol eta. Bulk was represented by B, Young's with Y, shear modulus with eta. So force upon area divided by change in length by length, similar to Young's modulus. So this is F L divided by A delta L. Exactly similar to Young's modulus. Again, so SI unit and that will be the same. SI unit will be that of pressure only, pascals only. Strain is unitless because change in length will be divided by the original. Write down this last one, third, shear modulus.
Shear modulus is denoted by that variable.
This symbol, this. It's like N with this elongated portion.
Okay.
This is not N. This symbol is called eta. All the Greek symbols, which are present, alpha, beta, among them this is. See, this question says that a 0.05 meter cube has its upper face displaced by 0.2 centimeter. It means some force must have occurred over here, and this instead has displaced 0.2 centimeters from here, and this length is 0.05 meters. So this is the original length, this is the change in length. Force applied is 10 Newton. And what will be the area of this displacement area? This will be side into side, that is 0.05 whole square. So eta, force 10 into length, original length is 0.05 divided by area is 0.05 whole square into change in length 0.2 into 10 to the power minus 2. See, this bracket will be cancelled. 5 into 2 is see, this is 10, then again 110 is left. Okay, force is 8 Newton, not 10 Newton. So this becomes 8 into 10 to the power 4 pascals or Newton per meter. Just check the calculation while you people are writing.
Ma'am, the area we take of the displacement.
Area of the upper surface is only taken, not the entire surface area. Or only the area of the upper surface is taken.
Okay.
This which has been displaced. This question says, two strips of metals are riveted together at their ends by 4 rivets, each of diameter 6 millimeters. What is the maximum tension that can be exerted by the riveted strip if shearing stress on the rivet is not to exceed 2.3 into 10 to the power 9 pascals? See, assume that each rival is to carry 1/4 of the weight. This means and here both of these are riveted together by 4 rivets. So force is being applied over here. Now see, I have assumed that F is the force applied on the metal strip. Force applied on the metal strip. So how much is the force on each rivet? On all of these fours, the force that is applied is F. So force on each rivet will be F by 4. So force for you is this. Now when we will be using this formula, F L by A delta L, you will put 4 also, because the force is F by 4. Fine. And what is the diameter? See, diameter is 6 millimeters. So radius will be 3 millimeters. So area will be pi r square. That is pi into 3 millimeter square. So length and here shearing stress and strain you will calculate. So see, shearing stress when we'll use, I think it's mentioned, no? Shearing stress is already mentioned. Shearing stress, theta is already mentioned as 2.3 into 10 to the power 9. This is shearing stress. Now see, eta is equal to FL divided by 4A delta L. Out of this, force, this term, force per unit area. This is already stress. When we are talking about shearing stress, this is force per unit area, which is already given as 2.3 into 10 to the power 9. So theta is equal to F by 4A. Can we calculate force from here? What is the maximum tension? So we have to find out force only. So force will be equal to 4A into theta, because length and delta L were already not given. 4 area will be pi 3 into 10 to the power minus 3 meter square, pi r square, into 2.3 into 10 to the power 9. This much of Newton is the answer. Just calculate, let me know whatever value you are getting. Now we'll start with stress strain energy.
Ma'am, so here the tension is the force.
Yes, tension, the question is asking you to calculate the force only.
Okay. Ma'am, so is this the tension for the whole strip or for each rivet?
No, the force that we have calculated, this is for all the rivets, because force on each is F. So if you want to find it for one rivet, this has to be F by 4. Okay, because we have assumed it to be F.
Okay.
See, actually, it's just that we have already multiplied 4 in our answer. If you remove this 4 and you will divide it here, that will be divided. So this part that will be left will be for each. But since we have already multiplied it 4, so that is for all the 4 rivets.
So for the whole strip, we just take it as F.
Yes, the total force that is acting on each of them. When we have added all those, that we have assumed to be F. F is the total force.
Okay.
Harsha was getting an answer also, no? 2.59 into 10 to the power 8 Newton. Okay. Please, someone else also. Let me know what's your answer coming. Okay, coming to strain energy. See, what is meant by strain energy? Strain energy, whenever we talk about this term, strain energy, this is basically work done. Whatever work, energy, and power you have done, strain energy is the simple amount of energy itself. That is known as strain energy. Now, strain energy here is one thing that is important, that energy density, we more than simple energy, we refer to energy density over here. So when a body is strained, work has to be done to deform the body. The work done is stored in the body in the form of elastic strain energy. Fine. Now, basically this strain energy is half into stress into strain into volume. Now see, class, if I bring this volume here, then I'll be left with half stress into strain. Half stress into strain. I'll be left with this. So this is what this is, energy per unit volume. This is energy density. So half stress by strain is the more common formula which we use and represent it with this letter. U is for energy. This type of U is for strain energy. Now you have a concept which is known as Poisson's ratio. What is meant by Poisson's ratio? Poisson's ratio's formula is similar to that of strain. Basically, what is meant by lateral strain, you should understand. There's a term which is known as lateral strain. See, when a body changes in length, it's not only necessary that the body's length is only changing. It can also occur if there was a thick let's say rod or a thick body, and because of change in length, the area is also changing. So what is happening? There's a change in diameter. So the change in diameter by the original diameter is known as the lateral strain. And lateral, why is the term lateral mentioned? Because this occurs laterally. That is, always it occurs sideways. This occurs sideways. Fine. So because what happens mainly is that when the length increases, the diameter decreases. Why? This happens in order to let the volume remain conserved. Volume remains conserved over here. That's why this is done. Nextly, so what is Poisson's ratio? You know what is longitudinal strain already. Lateral strain was something different. So lateral strain, I've told you. Longitudinal strain, you already know, that is the change in length is also occurring. Change in length by the original length. So Poisson's ratio is basically change in the lateral strain by the longitudinal strain. So sigma, we represent Poisson's ratio by the symbol sigma. So sigma is equal to lateral strain. Lateral strain, I have told you, minus delta d by d. So if I'm using the term minus, it means the diameter is decreasing only. Fine. Not increase in diameter. If there is any increase in diameter, we'll use the plus sign. So usually it's decrease in diameter only. Minus d by d divided by delta L by L. So sigma, this becomes, forget minus sign, right? Or keep it also delta d into L by delta L into d. This is the formula that we'll be using. Now, few terms which you should remember. Poisson's ratio is never more than 0.5. So if by chance your answer is coming more than 0.5, this means your answer is incorrect. It cannot be more than 0.5. Usually the answers come like 0.321, 0.249, 0.3, something like this. So mostly in between 0.2 and 0.4. So Poisson's ratio is never more than 0.5. Its value is usually between 0.2 and 0.4. This I told you. Now, class, this was Poisson's ratio. We'll see the questions, but before we see the question, Y is Young's modulus, B is bulk modulus, eta is shear modulus, sigma is Poisson's ratio. These are just few formulas, just in case if this helps you in anywhere for your entrances after class 12th, many people will attempt, or helpful for your 1-marker questions to get the answer very quickly. Wherever, that's why I've written all these relations. Young's modulus is 3b into 1 minus 2 sigma. Y is equal to 2 eta into 1 plus sigma. Sigma is equal to 3b minus 2 eta by 2n plus 6b. 9 by y is equal to, this is important. This I think you should remember, because this combines all these three. This you should remember, but rest of it, see, you have to solve the questions subjectively. You have to write everything. So this is not so helpful for you. But for your just only numericals where you just have to write the answer itself and do not show the working steps, for that case, it's beneficial. Fine, question we'll see later on. First, write down this.
Ma'am, in the second line, both the U's are not same.
No, this is smaller U for energy density, energy per unit volume. This Q is for energy, the way we have been using for potential energy. See, it says when a brass rod of diameter 6 millimeter is subjected to a tension of 5 into 10 to the power 3 newtons, the diameter changes by 3.6 into 10 to the power minus 4 centimeters. You have to calculate the longitudinal strain and Poisson's ratio for brass, given that Young's modulus for the brass is 9 into 10 to the power 9 Newton per meter square. What is the diameter of the rod? 6 millimeters. So radius will be 3 millimeters, that is 3 into 10 to the power minus 3 meters. Tension, which is equal to the force, is 5 into 10 to the power 9. 5 into 10 to the power 3 Newton. Now, what is the change in diameter? 3.6 into 10 to the power minus 4 centimeters. So this becomes 3.6 into 10 to the power minus 6 meters. Minus 4 centimeters, minus 6 meters. And Young's modulus? Nine into 10 to the power 9 Newton per meter square. So from Young's modulus, we can calculate longitudinal stress by longitudinal strain. So Young's modulus will be force. What is longitudinal stress? Longitudinal stress is force per unit area, and longitudinal strain, I'm writing it as it is. So what will be the longitudinal strain equal to? Force upon area. Young's modulus will come here. And area is also pi r square. And this is Young's modulus. Now see, you just have to substitute in the values. So longitudinal strain will be, see, force is 5 into 10 to the power 3. Pi is 3.14. Radius was 3 into 10 to the power minus 3 whole square. Young's modulus was 9 into 10 to the power 10. 10 to the power 10. Now lateral strain. Whenever you are calculating the lateral strain, that is minus delta d by d. So lateral strain will be minus delta d by d. What is the change in diameter? 3.6 into 10 to the power minus 4. No, minus 6 meters. And diameter was 6 millimeters. So 6 into 10 to the power minus 3 meters. So this will be.
And we don't use the minus. No, we don't use the minus.
Minus, this minus sign.
Yes.
This I told you, this is just showing that diameter is decreasing. So putting here has no significance. This just tells you that the diameter is decreasing. That's why I've also written it here. You can ignore it here. You can even omit it in the formula also.
Okay.
So this is 1. No, this is not 1. This is 0.6 itself. So 6 into 10 to the power minus 4. This is what? This is the lateral strain. So you've calculated the longitudinal strain, you've calculated the lateral strain. Now coming to Poisson's ratio. Poisson's ratio is basically lateral strain by longitudinal strain. So sigma is equal to, lateral strain is 6 into 10 to the power minus 4 by longitudinal strain. Okay, this has to be solved. 981. 2 something you should get. 2 into 10 to the power minus 3. 3.14. So 9, 9, 27, 5. 1 will come here, then 0. So decimal. Then 3, 9. 1.9. No? So 2 around something. So when 4 is left, so 10 minus 4. You get 6 into 10 to the power 1 0 I had already taken no, from here. So 1 will be left, 26 cancelled. So minus 3 it should be. Please someone cross check. I've just done it orally. It might be wrong. So this will be 1.96 into 10 to the power minus 3. So sigma will come 2. It's almost 2, no? This will be around 0.3 something, 0.31 something. If I take it as 2. Because 110 will be left, 10 to the power minus 1. Like this. Write down the solution and someone please keep on cross-checking the values. if you